Hey there, physics students. Today we're going to do electric fields and potentials together, and I'm your lab partner. If you haven't read the portion of that experiment in your lab manual, now's the time to do it. This video isn't a substitute for the manual, so you'll definitely want to go over the manual, read it carefully, and then come back to the video. Also, I want to mention I'm going to be playing the role of just some guy you've been paired up with in the lab. So the theory behind the concepts presented in this experiment will be gone over by your instructor. I will say a few words from time to time that I guess a typical lab partner wouldn't, but the fundamentals will be taught by your lecture or lab professor. So with that said, let's briefly go over the equipment that we have today. Digital multimeter. You're going to be coming across this instrument further on in the semester, and you'll be using it to measure such things as voltage, current, and resistance. For this particular lab, we are going to use it as a voltmeter. And we also have a power supply, which is nothing more than, say, well, we're using it as like a battery. We want to apply a potential difference between 2 points. And this is an adjustable power supply. For this particular lab, we're going to set it at 10 volts. This here is conduction paper, and there's a simple circuit mounted on this board here. I'll explain in a bit why we need that. We also are going to be using a galvanometer. What this does, it detects current, specifically small amounts of current. An ammeter detects current or measures current, but a galvanometer is primarily used as to detect the current, not necessarily measure it. That's why most of them don't have units associated with them. This one happens to, so I guess you could use it as an ammeter, but nevertheless, a galvanometer detects small currents. And what we also have is a couple of pencil probes. So we have this pencil probe here. If you apply a potential difference between these 2 points, a current will run through the graphite. And the same with this one here. Between these 2 points, a current will run if there is a potential difference. So these are our instruments we're going to use today. So the question is, what is the purpose of this lab? What we are going to do is investigate electric fields. So suppose I had a point charge here in space. It would generate an electric field surrounding it, and it wouldn't be too interesting. We could represent it by a bunch of arrows just radially pointed inwards towards that charge, or outwards, depending upon if the charge was positive or negative. So that isn't a very interesting case. If you had several different charge distributions with different charges on them, the field that it would generate would be very complicated. What we're going to do is set forth something in between. We are going to attempt to map out the electric field generated by configuration of an electric dipole. So an electric dipole would be a positive charge and a negative charge. We're going to have of equal magnitude and look at the electric field it generates. In fact, I'll flash one on the screen right now. So take a look at it. So if you notice, there are a bunch of arrows in a bunch of different directions, and what those arrows represent are the electric field. In fact, if you were to place a positive test charge on one of those arrows, it would follow the path of that arrow. That arrow is like a force. Well, it is an arrow that represents the electric field, but the force is proportional to that field. let me say a quick word about electric potential. Say I attach this power supply to this simple circuit here, making this point a different potential than this point. Let's say this point is a lower potential, let's arbitrarily call it 0, and this point is a higher potential, let's call it 10. 10 volts, voltage is the unit in which we measure potential. What would happen is that current would flow from the high potential down this circuit to the lower potential. And what you can do is think of it like the gravitational field the Earth creates. So if I was to put a ball up here, this is definitely at a higher potential than this point in space right here. So if I release the ball, it would fall towards the lower potential. Furthermore, as I lower the ball to different points in space, those different points in space have a lower potential than the higher one, okay? Likewise, with electric potential, whenever you cross a resistor in a circuit, the electric potential gets smaller. So these, of course, are new concepts to you, and you'll go over them in more detail as you progress in the semester. But I mention that because that is the purpose of having this little circuit here. It's actually called a voltage divider, and what we're going to do is set up a potential difference between both ends so that we can, at our will, select different voltages between this range of, say, 0 and 10. So I'm going to set this to 10 volts. And in my analogy with the Earth's gravitational field and potential, I made this the higher potential, and that's the lower potential. But since these are numbered 1 through 10 already in that order, I am going to make this the lower potential and this the higher electric potential. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 11 resistors in this circuit. It'd be easier, or not easier, but I like nice round numbers. I'm going to switch this up one notch so that we're only dealing with 10 resistors. Now, if the potential drops as you go from high electric potential to lower electric potential, every time you drop across a resistor, it's going to drop by 1/10 of the total amount, assuming that each resistor has the same value, that they all have the same resistance. And these all are the same resistor, or they all have the same value. Well, actually each resistor has a tolerance associated with it, so they're not going to be like dead on. I mean, you could spend a lot of money and get them more accurate to their whatever rating they have, but I don't know what kind of tolerance these have. So we're not going to get an exact 1/10 drop as we move across the circuit, but that doesn't matter. That doesn't concern us. As long as we know exactly what that drop is, we're good. And that is where our digital voltmeter comes in handy. What we'll do is manually measure that. So let's go ahead and measure that now. It's already on volts, DC. If you notice, I'm getting a reading of 10.2 volts. This is at 10. I would trust that, the digital multimeter, more than I trust this display here. So the total difference, potential difference between this whole circuit here is 10.2. What I want to know is, what is the difference between this point and that point? It is 0.898. So let us record that. By the way, I hope this isn't confusing. I know this is brand new to some of you. I talked about how as you go across a circuit, the voltage drops. That's from positive to negative. So as we saw, this was 10.2. If I plug this in here, it should drop 1/10, making it what, about 9 volts? And it definitely does. You know what, I apologize. I didn't realize we're getting glare. So you can see, I went across one resistor and it indeed dropped down approximately 1 volt. So this is part of our data collection. What we're gonna do is determine what the voltage difference is between this point here, which is, we'll call it our ground. Well, let's just call it our 0. So when I plug into this terminal, I'll call it number 1, and the voltage across that one resistor is 0.899. So I'm going to try and write with my left hand. That's not going to work. That looks horrible, and you can't even see it. So what you should do is record this data as well. Now, as I move this down, the voltage between here and the second terminal is 1.97. As I move down again, it is 3.09. By the way, eventually we are going to plug one of those pencil probes into these various plugs here and investigate the field with these different potentials. So that's the purpose of this simple circuit, this voltage divider. Next one, 4.15. 5.13. 6.14. 7.04. 8.14. 9.04. I'm compelled to double check that one. Yeah. And the last one, and again, that one is 10.2. That's across the whole circuit, 10.2. Okay. So, if I'm not mistaken, our digital multimeter is no longer going to be in use. That was its purpose. Now what I'm going to do is create that electric field that we saw from those 2 charges, the one I flashed on the screen. So here are our 2 charges. What I'll do is I'll make this the positive charge and that the negative charge. So we have an electric field, not necessarily, well, we're going to look at the two-dimensional case. We have an electric field that is permeating throughout this conductive paper, and we're going to map it out and see how close it resembles an electric dipole. And according to our lab manual, the first thing that it instructs us to do is map out equipotential lines. And what they mean by that is, well, if I was to arbitrarily test this point here and see what its potential is, it would be, in general, different from some other point over here. But there are going to be places on this paper where the potential is the same, and we're going to map those out. And we do that with our pencil probe. So what I'm going to do is connect our pencil probe to our galvanometer. And in turn, connect our galvanometer to one of these points here on this circuit. Now, let's see. We'll do we'll start with number 1. So, this end here, or I should say both ends, are at 0.899 volts compared with the potential of this guy here. So if I was to place this pencil on this paper and there exists a potential difference between this point and that point, current would and if you could see that galvanometer, let's zoom in a bit. There is movement. Slight, but there is movement. So what I want to do is find on this piece of conduction paper a point where the galvanometer measures no current. So I'm going to move this pencil around and look for a point where there's no current. As I move to the left, the current gets larger. What's difficult is that the camera is kind of in my way. I can't see if the needle is moving. So let me move things around. Okay, I shifted the camera around a bit. Now I can see our galvanometer better, and hopefully you can as well. When I touch this pencil to some arbitrary point, say here, the needle on the galvanometer moves. It moves to the left, and well, it's picking up a current. So the potential at that particular point on this paper and the potential on the other end of this galvanometer is different. There's a potential difference. Therefore, there's a current. Whenever there's a potential difference across a conductor, you will observe a current. So I'm going to move this pencil around until there is no current. So the needle went to 0. So at this particular point, there's no current going through the galvanometer. So I'm going to draw a little X on the conduction paper, and we can ask ourselves or remind ourselves, what is the significance of this particular point on the conduction paper, other than it has no, other than there's no current when I touch the tip of my probe there? What does that imply? Well, this wire here is at a potential of 0.899 volts. The other end of this pencil is a potential of what? We can surmise that it's at the identical potential. For if it wasn't, a current would flow from the paper through our galvanometer back out through here. So what I'm going to do is find another point that has the same potential as this point, 8.99. So that point wouldn't be it, because the galvanometer again is registering the current. I'm going to move the pencil to my right, and it's dropping, dropping, dropping. Right there is 0. So I'm going to draw another little X there. Start here. There's a bit of a current. I mean, by the way, I can move it in this, I can move it to my left, but the current is getting larger. So that isn't really going to help us find the spot of interest. So I'm going to move it to the right. It's not really going to 0. So I'm going to move it down. Now we're going to 0. Actually, we passed 0. Current is now running in the opposite direction. So I'm going to back up a bit, and we're right on 0. So I'm going to make a little X there. And in the interest of time, what I'll do is I'll make a few more X's. I'll stop recording, make a few more X's, and then get right back to you. Okay, we are back, and what I did was I made several, I marked several locations where there was no current. I'm gonna guess 25 different little X marks, maybe 30. Then I connected them with a dot. So you can see that little circular path there. That is a equipotential line. That line represents points that are at the same potential. And again, we know that because whenever I put my pencil probe there, I get no current. Previously, we're on 5 milliamps. I switched this down to a more sensitive scale, 50 microamps. So you can see if I touch this point here, it really jumps. And I am only like 3 millimeters away from my equipotential line. And as I move closer towards it, the current drops, eventually getting to 0 when I'm on top of the line. And if I keep moving in that same direction, I pick up a current again, but now in the opposite direction. And I'll leave it to you to contemplate why the current runs in a different direction after all is said and done with our nice mapping of this field when we're finished. So if I go around the circular path, you are going to see some movement on the needle, but that's just because my hand isn't completely steady, but it is centering around 0. And if I if I get to one of these X's that I mark, if I get right in the center of the X, it would indeed go to 0. So depending on how accurate you want to do this, yeah, you know, it would take a bit of time, and hey, I like accuracy. That's why I'm pausing the video and taking my time finding some of those X marks. So what we've done is found our first equipotential line. So I'm going to call this nothing better than V1. And I'm calling it V1 because we're plugged in here to the slot we labeled as 1, which was again 0.899 volts. So let me just say once again a few words about this galvanometer. We have these two ends here. The other ends are connected to our galvanometer. So our galvanometer is in between these two ends. So if a current flows from here to here, it's flowing right through our galvanometer, and our galvanometer is doing its job and detecting that current. So if I plug one end to our number 1 slot, I know that this is at a potential of 0.899. So now let me apply a potential to this end. I don't want to break the thing. The scale is too sensitive. You saw how the needle jumped. A current is flowing. So I know that there is a potential difference. Move the pencil towards this equipotential line. Right when I get on it, there is absolutely no current detected by the galvanometer. So I know that the potential at this point is identical to the potential on the other end. So I know that the potential on that X mark is 0.899. And all of the other X marks are 0.899 because I measured no current. So this could be a little tedious, but what we do now is find our next equipotential line by setting one of the ends of this simple galvanometer probe circuit to a different potential. I moved it to slot number 2, which, if you recall, is at 1.97 volts. So now let me touch our paper again. I have a little bit of a current there. The needle moved, so I'm going to move this towards this brass washer here, and it's going down to 0. So right there it's 0, and I'm going to draw a little X mark. Put the probe here. I'm getting a current. I'm going to move the pencil closer to that brass ring, and it drops down to 0. So I'm going to make a little X mark. And to reiterate, the purpose of this is to find the potential at particular spots in the conduction paper. I know for a fact that at that X that I just drew, there is a potential on this conduction paper of 1.97 volts because no current flows through the galvanometer when I place the tip of the pencil there. It is at the same potential as this end, which again is at 1.97. So I will pause the video and draw some more X's. So here is our second equipotential line. I labeled it V2. And we could say now that the potential along that line, if I were to indeed connect all those X's together and there was a line, it would all be the same, and it would be 1.97 And again, I know that because if I touch this probe to say here, we get a current. If I move out away from that line, we get a larger current. So let me move towards it. You can see the needle on the galvanometer is getting smaller and smaller. And when I hit this area where a line should be between these two X marks, the galvanometer picks up 0 current. So the potential at this point is the same as the potential on the other end of this galvanometer, which is 1.97 volts. Now, if I want, I can go back to my original V1 and touch this pencil probe on that equipotential line, and you can see how the needle jumps. Let me change the scale here. See how that needle jumps? Well, what happened a few minutes ago when I touched the probe on that equipotential line? There was supposed to be no current. Well, the answer is that when I found that equipotential line, the other end of the probe was plugged into this port number 1, which was at 0.899 volts. It's now at number 2, which is 1.97 volts. And of course, there is a potential difference now. What was the potential on this equipotential line? We determined it to be 0.899, and now the other end of this probe is at about 2 volts, 1.97. So there is indeed a potential difference, and a current does flow, and our galvanometer does pick it up. But if I was to switch this back to 0.899, the galvanometer would read 0. So let's move this on down to number 3 and find yet another equipotential curve. And I will pause the video. So I'm in the process of finding our V3 equipotential line labeled V3. And I found a point here, I found a point here. And if you notice, if I continue to go around this washer in the same fashion that the other equipotential lines were drawn, I get a current, and I can't seem to get rid of it. So if you were doing this, you would just have to be patient and move your pencil around a broader area. For instance, I just found it now, it's at 0, and I already marked that X. And as you move to another point, you'll find that it veers off towards the bottom of the page. So my last point is right here. If I move to my left, let me put this on a more sensitive scale. As I move to the left, you see we induce a current. If I move to my right, we induce a current as well, just in the opposite direction. But when I'm right at this point, that point where I made a dot, we are at 0, no current. So the potential at that point is 3.09. So 1, 2, 3, 4, 5, 6, 7. I have 7 points there. And I'll pause the video again and finish those up. In fact, maybe I should just draw them all. Furthermore, instead of outlining them with the pencil, we'll use a China marker and it will show more clearly. Let me just jump ahead to number 9, or spot number 9. If I put this, let me lower the scale. Here, I get a little current. Moving this pencil all around in this area does not bring it down to 0. So the potential that pertains to 9.04 is nowhere in this area. So I move the pencil along here. I could see it's dropping. It seems like it wants to go to 0, but it's not quite there. Now as I move towards this brass washer, it is going to 0. In fact, if I get too close to it, it passes 0. Now there's a current in the opposite direction, so let me back it up a bit. And I'm not directly facing the galvanometer, so I can't tell if it's right on zero or not, but it's going to be somewhere in this area here that I get no current, which means at that particular point, the potential is 9.04. So let me go ahead and draw these lines. Typically in the lab, this board is laying flat on your desk. But for the purposes of this video, in order to get the instruments and this board all on the screen, I propped it up on this little stand. So what I'll do is I'll unclamp it, lay it flat, and knock out all these lines in 10 minutes, 15 minutes or so, and outline them with the China marker, and see you then. Okay, so I just finished drawing out the remaining equipotential lines. Let's take a look at what they look like. Now, I'm gonna put this camera at a slight angle, and the reason I'm doing that is so that you could see them better. If I put it straight on, there's a bunch of glare. Okay, so there we are. And let's talk about it. We had 10 different ports, so that should have given us 10 different lines. But if you notice, I only have 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. As it turns out, I couldn't get a 10th one. Well, what happened was the 10th equipotential line is underneath this washer. So I didn't draw it. And why is that? Yeah, it could be a number of reasons. First of all, these resistors aren't identical to each other. So the voltage drop between 0 and the first port is different than the voltage drop between the 9th and 10th. So although V1 is here, my V10 isn't. It's underneath. So there's several reasons. Another one is that washer. There's like this groove underneath the washer that can be worn down, altering the conductivity in that region. But anyway, it doesn't matter. We have 9 equipotential lines, and there they are. As we should. Notice our V5. Our V5 is right down the middle, giving us 4 equipotential lines to the right and 4 to the left. Of course, if we added one more, it would be underneath that washer. For if we added another to this side, it would be underneath the washer as well. Okay, well, that solves that problem. Anyway, there you go. That is the first part of the lab. And at this point, you may be wondering, well, wait a minute, that doesn't look like the field you talked about at the beginning of the video, let alone that diagram you showed us. Nor should it. This isn't a depiction of the electric field. It's a depiction of the potential. And our next step is to draw field lines. And we are going to do that with the pencil compass probe. So with this probe here, what we do is touch this to the conduction paper, and these 2 points are connected to our galvanometer. So if these 2 points are at a different potential, a current will run through the galvanometer. And according to our lab manual, there should be maximum current right along an electric field line. Okay, bear with me. This is typically just laying flat on your desktop. So this may be a bit challenging to do while it's horizontal or vertical here. Okay, here we are. We have a different view of the board. I was going to give you a bird's eye view, but I put you at a slight angle because you can see the China marker, the equal potential lines, much clearer. There's too much glare if you're looking directly overhead. But anyway, there you go. And I forgot, I wanted to mention, I removed the tape on the bottom of the paper. And I wanted to do that for a reason, so that you can see in more detail how those lines, how they behave at the edge. Up on top where there's paper or tape here, well, I guess maybe they look the same to you, but I just wanted you to see exactly how they intersect the edge. Furthermore, if you were to shrink the size of this paper, just give me a second here. I'm looking for some tape. Let's say we were to shrink the size of the paper. Like say, to a different dimension. Let's say where I put that new tape, that's where the paper ended. You could see that the lines intersect the new edge, not all in the same way as they do with the original paper. So I guess what I'm trying to point out is it just coincidentally the dimensions of our conductive paper coupled with coincidentally how much voltage we put across this circuit here and chose to measure out that makes these lines intersect that edge at in that particular way? It's not a coincidence. Clearly, whenever you shrink the diagram, the lines don't always intersect the edges in the same way. So the question becomes why? And I won't elaborate on that anymore because I believe your lab manual does ask you a question about that. So we're going to use our pencil probe again. And I'm on an equipotential line, V2, and you can see that the galvanometer is picking up no current. I will rotate it, and a current begins to flow. between those two tips of my probe. Now, right now, I'm at a slight angle looking at that galvanometer, but it looks to be like 11 or so. And I keep rotating it. It's getting larger, larger. Now it looks like it's getting smaller or decreasing as I rotate it. It's definitely decreasing, so I'm going to go the other way. And I'm going to quit while I'm ahead. The camera's kind of in my way. I'm doing the best I can to hold this steady, but it looks like we found the point of maximum current, or as the manual calls it, maximum deflection. I guess they're speaking of the needle on your galvanometer. So if I could find my other probe just to use as a pencil. I'll mark that spot. Let's move on over to V3. Both tips of the probe are on an equipotential line. So of course I'm getting no detection of current. I will rotate it. I'm picking up a current. As I rotate it, it gets larger and larger in magnitude. Now it's getting smaller, so I'm going to back up a bit. Looks to be right there. And we'll do it with one more line, say V5, that straight line right down the middle. If I put both tips right on the line, it's 0. Now it's starting to move down. Now the needle, the current is getting smaller. So I'm going to back up a bit. Let me find it. What's somewhere in that area right there. So what we just verified is that the maximum deflection of that needle occurs in a direction perpendicular to the equipotential lines. And our manual tells us, and you'll learn more about this later, or maybe you already have in your lecture, that the maximum current will indeed occur along an electric field line. So what we've done is we've just convinced ourselves that maximum deflection occurs at 90 degrees perpendicular to these equipotential lines, and we'll now map out, I believe the manual suggests, what is it, three electric field lines that connect the two different charges. And all we need to bear in mind is that whenever we cross an equipotential line, that electric field line that we're drawing must cross it in a particular fashion, right? And what's that? Well, 90 degrees to it. So give me a second here and I'll go ahead and draw some sample lines. Okay, ladies and gentlemen, let's wrap this up. We're almost done. Take a look here. And what we did was sketch out a few sample electric field lines. And I disconnected the board from the power supply. Remember, that was the positive charge, that was the negative charge. The electric field lines always run in a direction from positive to negative, hence the arrows in that particular direction. By the way, you might wonder, well, I know that this field line intersects this equipotential line at a 90-degree angle, and as well as this one here, but how do I know how it behaves in this region? Well, what you do is painstakingly go from here to that point and swivel this around. Of course, this would be hooked up to your galvanometer and mark where the maximum deflection is, and I found it to be there, so I marked that location. Then I moved this over and did it again. Swiveled this around for maximum deflection of the needle, maximum current flow, and found it to be there. So then moved it again, swiveled it. You can see all my little lines there. So that's how I determine the actual path of that electric field line. And then like once I got to around there, I really didn't need to do the second half. It's symmetrical. The one in the middle, I did go across just for the heck of it, but it turned out it's just a straight line. So there you go. A sketch of 3 different electric field lines. And the last thing I want to point out is those points I labeled with tape. Actually, I labeled them point A, point B, point C, and point C, but I spelled out point with a pen, a little ballpoint pen. You may not be able to make that out. So I went over and marker A, B, C, and D. This data you will need for your lab report. Let's see. Point A, which is on an equipotential line, is right near point B, which is on a different equipotential line. And what I want to say is just that point A and point B are 0.9 centimeters apart. 0.9 centimeters apart. Now for point C and point D, those 2 points, again, which are located on different equipotential lines, are located 1.7 centimeters apart. So you'll find this information useful when you get to the section of your lab manual where it asks you a few questions. And that's a wrap. We're finished. This was fun, and I'll see you next time.